Okay, so today we will be talking a little bit about triangle congruence. Have any of you actually heard about what triangle congruence is? So triangle congruence basically means that two triangles are the same shape and size. So, for example, here you can see these two triangles, ABC and DEF, are the same shape and they're also the same size, or you can kind of see that they're very similar. They're basically the same. It's just that they're in a different place and they're basically the same triangle. So congruence, even if you spin it around or sort of move it around, these two triangles will still have the same shape and sides, right? And you can even flip it. You can even flip the triangle and it will still have the same shape and sides. Let's go through this again. Well, so basically a congruent triangle means that they're the same shape and size. And the way we express congruence, the way we express congruence, I'll just go from here. So the way we can express congruence is that we use these sort of three dots here. You see these three sort of lines all on top of each other. That basically means congruence. It's sort of like an equal sign, but with an extra line. So basically, these two triangles, ABC and DEF, are congruent to each other. And even if we get rid of, flip it over, it's still congruent. But over here, that means that they have the same side length and the same angles. Does that make sense? Because a triangle has three different angles and three different side lengths. So that's basically what determines, what a triangle actually is, right? So does anyone want to see if they know which triangle is actually congruent to triangle X, which is this triangle right here? Yep, Jasper says A, and yeah, that seems to make sense, right? Yeah. So Jasper and Loy say A, and that does make sense because you have the 4, 6, 10. Yeah, this is pretty simple, right? It's just saying that these two triangles have the same shape and size, same angle, same lengths, side lengths. But the thing is that you don't actually need to know every single angle and side length, right? So some of you might have heard of this before. So there's four types of congruence: SAS, SSS, ASA, and SAA. So what this means is that you only need to know, for example, for SAS, you can actually only know two of the sides and one angle to see if it's congruent. And you only need to know that those two are the same to know that the entire triangle is congruent. And we'll get into why exactly and a very good visual, like some visual representations of this later. But SSS, if all of the sides are the same length, then they're also the same triangle. And we'll see why that is later as well. Angle side angle, what this means, the reason why this is different from SAS, ASA means that you have a side and you know the length of one side, but you also have two angles jutting out from either side. So yeah, but unfortunately ASS does not exist, though it would be kind of funny if it does. And we'll also see why ASS doesn't exist later. But for now, we're going to look at SAS. So let's I'll share a different window. And this will help, this will make it a lot clearer because, all of these letters and SAS, ASS, it's kind of confusing, right? So let's have a look at exactly why SAS exists. So this is SAS congruence. And basically what this means is that we can adjust the length. We can adjust the length of this. So let's say we have an angle that is sort of set in stone here. What can we do? What can we do to these other lengths to make sure that it is the exact same angles and side length as the other one, as this triangle right here? So essentially, if all the side lengths are equal and all the angles are equal, then they're congruent. So if we adjust sort of this length right here to be 20, and this other length right here to also be 20, then notice how there's only one possible triangle you can create from this. So basically, if we have just DAE and this angle, there's only one possible triangle you can create from this, right? Just by connecting D to E. So if I say hide this and hide these angles, you can clearly see that there's only one triangle you can form, and that triangle is formed by connecting D to E. So essentially what I'm saying is that there's only one possible triangle that you can form if you know the side, angle, and side. And if you think about it, if you know that there's only one possible triangle that you can form, that also means that any triangles with the same side, angle, and side lengths, angle, and side lengths are the same. So does this make sense to everybody? It's a little bit, if I explain this a bit fast, it's totally fine if you want to listen to this again, hear about it again. But essentially, you can adjust this and notice how when you adjust it, there's only one triangle possible with the side and an angle. So basically, there's only one possible triangle that you can create with a side and an angle, and then a side sort of an angle sandwich between two sides. So does this make sense to everybody? You need a second to think about it. It's kind of hard to intuit just directly, but I will send the links to these GeoGebra files and if you to the chat later so that you can actually try this out for yourself, so that you can kind of see exactly why SAS congruence is a thing. So does anyone have any questions or sort of unclear parts of it? Because I did explain this a little bit quickly, so it's totally fine. Okay, so now we will move on to, so we'll say side, angle, side. We'll put this in the chat so that it's for reference. So this is the first type of triangle congruence that we can see here. And this kind of sets the tone for the rest of our proofs or our ideas about congruence, because if there's only one possible triangle you can create using this information, then that means that this is a way to create two congruent triangles. And that's the idea. So there's only one possible triangle you can create with side, angle, and side information, which means that all triangles with the same information for a side, an angle, and then another side have the same have the same angles and sides, because there's only one possible triangle that you can produce. So let's move on to a different kind of congruence. So let's talk a little bit about ASA congruence, which basically means angle, side, angle. Well, this is moving around a lot. So essentially what angle, side, angle means is that, delete that. Essentially what angle, side, angle means is that you have a side here of a certain length. And you know what the length of this side is, right? So what that means is that, but we also know the angles that come out of each of these sides. And what that means is that there's actually only one triangle possible here as well, right? Because if, say, I adjust this, the only possible triangle that you can create with an angle of 50 degrees, and let's find the length of this, and a side that's eight whatever units long, will actually just be, there's only this one triangle possible, and with these two specific angles attached to the side. And you can clearly see that even if I adjust the angles or whatever, you still only have one possible triangle. which means that since there's only one possible triangle, that means that all triangles with these characteristics, with a 37-degree angle and a 76.2-degree angle on each side of this 8, say, centimeter side length, is going to have the same other angles as well. All the other angles and sides are also going to be the same, which means that triangles, you can determine whether a triangle is congruent or the same shape and size as another triangle just by looking at a side and then angles on either side of that side. Now, for instance, however, you can also think about this, that angle side angle does not include, say, only having this other angle, this angle over here, because that angle over here is different, because that angle over there would actually be AAS or SAA, since that's a different order of the angles and sides. So we'll have a look at that later as well. But for now, does anyone have any questions about about angle, side, angle? Basically, the idea is that the angle, side, angle, or side, angle, side is the order in which these angles and side appears. So if there's an angle and then a side and then an angle, then you will know that these two triangles are the same. If there's an angle, side, angle sort of set that is the same, then we know that those two triangles have the same shape and sides, even if you rotate it. So does anyone have any questions about this, or anything that's unclear, or any comments as well? Okay, so let us move on to the next one, which, as mentioned before, was we can do SSSAA, which is sort of what we talked about before, and it's different from ASA. So, and I'll show you exactly how it's different. So in this case, we know the length that we already know is going to be AB. So we know AB is 9 long, and we know that there's an angle, a 60-degree angle and an 80-degree angle. But the 80-degree angle is not connected to the 9 unit long sort of thing. It's not connected to the 9 unit long line. And let's say that there's an angle that's 60 degrees and then there's an angle that's 80 degrees. So if we just continuously adjust this line right here, then you can clearly see that there's only one possible triangle that can be formed, right? Just look at it. So because we know that AB is going to be 9 units long, and we know the other angles, then all of this line is basically just going to have a specific angle from that other line, which means that there's only one possible place that it can attach to B, where this line actually meets B. And we can find that this other triangle, that the only possible triangle in this case would be between A and B, have a side length of 5.9, 80 degrees, 60 degrees, and 9. You can clearly see that there's only one actual possible triangle that can be formed in this case. So does this sort of idea make sense to everyone? It's going through these quite fast, so if you want me to re-explain anything, that's totally fine. Okay, what just happened? All right. So now we will talk a little bit about, I'll put this in the chat, side angle. little bit about the idea of, where is it? Of SSS. So what this is saying is that if you know the side lengths, every single one of the side lengths, all three side lengths, you can actually figure out exactly what the other angles are, because there's only one possible triangle. And this will actually tie back into the idea that triangles can be flipped or rotated or whatever, and they're still congruent, even as long as their angles and sides are the same, as long as their shape and size is the same. So what we have here is simply a circle. So we know the length of AB. So AB is a given length. So let's say that we have a length AB and we want to construct a triangle with two given lengths. Well, and we can have, say, AB, let's let AB just be 2.5, I guess. That sounds about right. And let's say we want to have another length be another 2.5. Actually, let's do 3, I guess. But let's say we have another one that is 3. So a circle is actually a really good way to think about this, because a circle represents all of the points, every single place, which is a certain distance from a center point. And in this case, the center point is B. So any point on this circle, let's say, like, I don't know, maybe this point right here, is going to be exactly 3 units away from B. And it doesn't matter if we move F around, it'll always be 3 units away from B, which means that if we put F here, then this length from B to F will still be 3. This length will be 3. And it doesn't matter, and it doesn't matter where we move F, it'll still have the same length. So this is a good way to see all of the possible places you can put it. But clearly we have two sides and we don't know exactly what the triangle is. There's an infinite number of possibilities, and all of those possibilities land the line. But here's the interesting part. We can actually, if we know the length of the third side, we can actually figure out exactly what the triangle is. So let's say we have a circle with radius, another side with the radius 5. So because this other side has a side length of 5, any point on this circle will also be 5 away from A, which means that the third point is actually going to land. So the third point is actually simply going to land right where these two circles meet, because this is where the third point will be both 3 away from B and 5 away from A. Does this make sense to everyone? The definition of a circle and how we can use this to prove SSS similarity, or congruence. Does anyone have any questions or see any problems or with this, or have any comments? So, however, in this case, there's actually a problem, because you can see that you can actually form two triangles here, right? Oh my God. You can form two possible triangles with a length of AB and with BF and with side lengths 2.5, 2, and 3. And so side lengths 2, 2.5, and 3. So because you can actually form another triangle here. There's actually 2 points where the circles intersect. But this is actually the same triangle, because these two triangles have the exact same side length, and angles. And we can simply look at that through the calculator, the graphing calculator, to 22.58, 22.5, 22.33. Okay. Basically, there is a little bit of error in my placement, but yeah, they will generally be the same exact angle. And yeah, so there's a little bit of error with my placement. I think I might have not put it exactly on the spot, but that's the idea. These two triangles are actually just reflections of each other. So it's reflected over each other, which means that these two triangles are actually the same triangle and have the same side lengths and angles. And because of that, there's only one possible triangle that you can form if you are given 3 side lengths. As such, this is SSS similarity. Congruence, sorry. Similarity is different, but congruence, SSS congruence, which basically just means side, side, side. You know all 3 sides, so you know the triangle. You can figure out what the angles are using other methods, but you know that there's only one possible triangle. There's only one possible configuration of angles if you know all 3 sides. So, and finally, we will move on to talking a little bit about what SSA is, or you could also call it ASS. It's about the order in which they are going in, the orientation that you know the values. So, ASS, will not be saying the name because it's a little bit, yeah, it's not the best word for this, but we can see that ASS, wait, this is the ASS actually, it's this one. Sorry, I'm gonna have to find that. Oh, yeah, it is this one. Okay, so ASS means that we know the angle, we know one angle, and then we know a side, and then we know the opposite angle. So we know that there's an angle, say 55.7 degrees. We know that 55.7 degrees is right next to a side of 3.06. And then on the opposite side of the angle, so on the other side of the triangle from that angle, we have a certain side length of 3.91. And what this means is actually, there can actually be 2 possible triangles. There can actually be 2 possible triangles in this case. So right now, there aren't actually 2 possible triangles. But if, say, we move A to be outside of the circle, or the circle representing all the infinite number of sides that it can go, or this 3.91 side can go, you can actually see that there's 2 possible triangles that may be formed. So we have this triangle, which is ADB, like that. We have this triangle, and this triangle has an angle of 55.7 degrees, a side length of 4.46 degrees, and another side length of 3.91 degrees. But we also have another triangle, which is ACB. ACB is a triangle that has a side length of 4.46, a side length of 3.91, and then an angle opposite of 3.91 of 55.7 degrees. There are 2 possible triangles that you can actually form if you are given a side angle sort of information. So what does this mean? What this means is that if 2 triangles have the same side angle or angle side information, you can't be sure that they're congruent, because there's 2 possible triangles. That means that it could, it could be congruent to triangle ADB, but it could also be congruent to triangle ACB. So there are 2 possible triangles that can be formed, which means that if you are given an angle, a side, and then another side on opposite of that angle, you don't know that it's actually congruent. So does this make sense to everyone? Angle side side does not exist. And I will send all of these, again, I will send all of these GeoGebra files, which you can access online to the Discord chat, WeChat, and on Zoom after this lesson is over. So you can try it out for yourself, because once you try it out for yourself, you will really understand. And it's actually kind of cool. It's like really interesting, I think, like the way these work. So let us just go back to the presentation. So we can clearly see that we have these 4 different types of congruence: side, angle, side, 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 angle, side, angle, and side, angle, angle. So next, we're going to think about how we can actually use this to figure out to solve some problems. So in this case, we have 2 triangles that are formed by 2 intersecting lines. So we'll just say that this line right here, this line from here to here is going to be from here all the way down to here. This line is just a straight line. It's just going to be a single line. And then also from here, this line is also just going to be a straight line, a single line. And we're trying to figure out, just based on these side lengths and the information that we're given, what the length of this side over here is. So I'll give you a second to think about it. And yeah, I'll give you a second to think about it. And if you have an answer, then yeah, please type it in the chat, or you can say it. And later we'll have a look at how we can solve this problem. So just remember that these 2 lines, this line and this line, these 2 lines are straight and they intersect at this point right here. Okay, so does anyone have any ideas on what the answer is, or how we can actually solve this? So the best way that we can actually start this is by looking at these 2 lines, which, if you remember, these 2 lines are actually straight lines that cross each other like this. So what that means is that there's actually a property which states that these 2 angles here are actually the same. these are actually the same angles. So these two angles here are actually the same. And we know this length right here, this length right here, this length right here, this length right here, and these two angles. So, does anyone remember which type of congruence we can actually use to see how we can solve this triangle? So, the idea that I'm trying to talk about right now is that these two triangles, the top triangle, this top triangle right here, and this bottom triangle are actually congruent. And does anyone know why they're congruent? What kind of properties these triangles have that we know that can show that they're congruent? So does anyone have any ideas on which property we can do? I think a good way to label this is just like by doing A, B, C, D, E, so that we can easily and better communicate our mathematical ideas. So does anyone know how we can solve this and how we can figure out congruence? What type of congruence we can use? Well, the idea is actually SAS, side angle side. So if you remember SAS means that there is a side, you know this length of this side, you know the side, and you know the angle between those two sides. There's only one possible triangle you can create using with this information, by just simply by connecting the ends of those two sides, right? So what that means is that we know this side length, we know this side length, we know this side length and this side length, but we also know the angles between them. So these ABC, triangle ABC, this triangle right here, has the same angle between the same two sides as DBE, right? Does that make sense? So these two triangles are actually congruent on SAS. So we can write that by saying ABC congruent, giant equal sign, DBE. It's kind of going off the page a little bit, but yeah, so ABC is congruent to DBE. And what that means is that, if you remember, congruent triangles have the same shape and sides on all of them. All of their angles and all of their sides are the same. But we also remember that you don't need to know every single angle and side length to be sure that they're congruent. And what this means is that these two triangles, because they're congruent, that means that all of the other angles and sides must be the same as well. So what does that mean that AC will have to be? What does this length have to be if we know that these two triangles are congruent? Does anyone have any ideas? Well, the right answer is actually 3. This length right here is 3. Let's remove some of that. Okay. This length right there is actually 3. And the reason is that congruent triangles have the same parts. All of the parts of two congruent triangles are the same. All of their parts. So their sides are the same, their angles are the same. So if we know that a congruent triangle is the same, has the same size and angles, then that means that all the other sides and angles are also the same, which means that we can easily figure out what AC is based on what DE is. And that means that AC is going to be 3. So does that make sense to everyone? Are there any questions, confusions, comments, concerns? So let us move on to the next question. This next question is quite a bit harder, but it is a similar idea and uses congruent triangles as well. So basically congruent triangles help us find out lengths that we couldn't have ever found out before. If we know two triangles are congruent based on a certain amount of information, a smaller amount, then we know what the rest of the triangles are, and we can glean new information from that. And that is the idea of why congruent triangles are so important in all of geometry and sort of just in general. And they're very useful in plenty of that aren't geometry, like science and proofs. I mean, even parabolas will involve it, but that will be for another day. So today, though, for this question, we will be wondering what this length is right here. That length right there. You know, maybe I should use a different color. Red, yeah. So what this length is right here. And in case you're curious, what this means right here is that J and K are parallel, which means that these two lines will never meet, and they are facing the same direction. And we'll talk about exactly why that matters later, but we will. Another piece of information that I think you guys should know is that these two angles, this sort of square thing right here, is actually just means that these angles are 90-degree angles. And all 90-degree angles are the same. So these two angles are the same because they're both 90-degree angles. And in fact, that is one of the axioms or the base assumptions of geometry. So we can safely assume that these two angles are the same. So I'll give you maybe 3 minutes-ish to think about this, and then we can kind of discuss and talk about it a little bit. It's a much harder problem than the other one. It's a bit more complicated, but I think it is quite cool. Oh yeah, and one last piece of information here is just that this line right here is a straight line. So it is a completely straight line. Okay, so does anyone have any ideas or thoughts about this problem? So Jasper says that it is 2, and sorry about that. And that, yeah. Um, do you have do you know why it's 2? Do you want to explain why it's 2? I think it is 2, but I also think it's 2, but Jasper, do you want to sort of talk about why you think it's 2? Yeah, so the triangles do look the same. So it does kind of seem like a, B, C. Let's just label the triangles, and D, E, F are congruent. It does kind of seem like this is true. But of course, we have to prove it, we have to see exactly why it's true. So the first thing we can do is say that we know that they share two angles. So we know that, whoops, we know that they share a right angle. So they both have a 90-degree angle. So they both have a 90-degree angle. And on the opposite of that 90-degree angle, both triangles have a side of length 3, right? You can see one here, and you can see one right here. So that means that we have an opposite side, sorry, of side 3. But we only have an angle and a side, and if you remember, all of these require more than just an angle and a side. It's side, angle, side, angle, side, angle, side, angle, side, or side, 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 and then angle, side, side doesn't exist. But basically, we need more information. But we're actually given more information, right? Because we know that J is actually parallel to K. So sorry if this wasn't clear, but J is actually this line, big line up here, and K is this bottom line down here. So these two lines are parallel. And what's interesting about parallel lines is that there's actually a property of parallel lines which states that if you have a parallel line, then let's extend this line right here. Whoops. Let's extend that line right here. So if we extend that line, we know that this angle, this angle down here is actually going to be the same as this angle up here. So because if we have two parallel lines, these two angles will be the same. Does that make sense, everyone? Do you guys have you guys learned about this in school? Or it's a property of parallel lines, and you can kind of think about it by saying that parallel lines, basically you're just moving the parallel line up and down. A parallel line, if you're trying to make two parallel lines, they're just moving up and down. They're not rotating. So if they're not rotating, then they're not actually going to change the angle with the other line, right? So they're not actually rotating. But what this means in this case is that BAC, or this angle right here, is also going to be the same as this angle down here. Because this angle right here has to be the same as this other angle here. This angle here has to be these two angles have to be the same because they're kind of like opposites on intersecting lines. Like this angle here is going to be the same as this angle there when they're intersecting. So what that means is that BAD, this angle, is going to be the same as that angle. And what that means is that we actually know that we have another angle here. So we actually know that these two angles right here are the same. Does that make sense to everybody? Do I need to explain this again? It is kind of a logical leap. You have to think about it a lot more than the other problems, but I think it is quite cool. I'm not gonna lie. I think it's pretty cool. It's a pretty cool way to see this problem. So if that makes sense to you guys, that this angle right here is the same as this angle right there because of parallel lines, the properties of parallel lines and angles, which is basically just saying that this angle right here is the same. These two angles are the same, like that. So there's no other like, oh, yeah. But now what we have is let's just erase this. Oops. Now what we have is we know an angle, we know this angle, we know an angle is the same, we know a side opposite to that angle is the same, and we know a side, an angle next to the original angle is the same. So we have an angle next to an angle next to a side, also known as AAS, or you could also say a side next to an angle next to another angle. So in case you can check the chat, and side angle angle actually does constitute congruence. And if you remember, it's because if we have a line here and we have a certain angle, there's only one possible, and we have another certain angle, there's only one possible length of this side right here that will actually create a triangle. Otherwise, it's not really, it doesn't create a triangle. There's only one possible length, which means that there's only one possible triangle, which means that there's actually SAA is congruence does exist. And that means that, which means that these two triangles, ABC and EDF, are congruent. They're the same triangle. They have the same sides, the same length, they have the same side lengths and the same angles. So does this make sense to everybody? Does it have a, does like the logical leaps that I have made, or like the logical, the logical ideas that I have put down make sense to everybody? It is quite like a couple steps ahead, and I think that if you wanna sort of get the hang of it, you should just try some of these problems. They're actually quite fun and slowly they'll get harder, and eventually you'll actually be able to use it for a lot of other different really interesting problems, and even in the real world. But anyway, so does this make sense to everyone? Is there any problems? Any ideas? Okay, so let's move on to a real life example of how we can use this. Because in the real world, it's funny, because in the real world, we actually live in 3 dimensions, not just 2 dimensions. Because here, we're just looking at 2 dimensions, it's sort of on a flat screen, but the real world, we have 3-dimensional, it's 3-dimensionality. We have 3 dimensions, so we can actually move up and down, left and right, forward, backwards. And yeah, it's pretty self-explanatory stuff. But let's think about something. So, basically a long time ago, there was a general who wanted to cross a river, and he kind of wanted to see how far it was to the other side of the river. Well, actually didn't want to cross it. He wanted to bombard the other side of the river with cannons. And in order to do that properly, because there were the enemy troops on the other side, he needed to see how far across, how long that river was, or how wide that river was. So basically what he wanted to see was what AC is. And he had this sort of device that could measure the angles as long as he stood up and stood still. It could measure the angle to the ground or to something else. And in that way, he could measure this angle, which is ABC, to the other side of the river. He could adjust the device so that it goes to the other side of the river, and so that angle points to the other side of the river. And when this person stood up, he knows his own height. He can measure his own height, but he can't measure the length of the river because he can't, like, he doesn't have a boat or something to measure across. And also, if he tried to do that, get shot at by the enemies. So basically what he did was he decided that he could measure the angle here, and he knows what his own height is. He knows how high the device is going, measure the angle from his height all the way down to the other side of the river. And he also knows that he's standing at a 90-degree angle from the ground, right? Because humans, we stand exactly perpendicular to the ground. We're standing up perpendicular to the ground. And now now he had a pretty smart idea to sort of just rotate himself, to move himself around so that we can get from BAC, this triangle, and sort of basically just reflecting this triangle onto BAD. So rotating the triangle around, and he just rotated it 180 degrees all the way around. And now he now he could see this angle right here. And now he could see exactly where on the ground that could point. And because he knew where on the ground that pointed, because he knew the location of D, because these triangles are congruent, and because these triangles are congruent, we know that there is a ASA congruence between this triangle and this triangle. Because we know this length right here, we know these two angles, and we know these two angles. And because they are congruent, that means that he can easily figure out where this point is by sort of just rotating himself around and just looking down with the exact same angle. And then he can find this point and find the distance between himself, his original location, and that point. So basically, he can find AD. And he can do this because it's on land, and it's on his military, his army's side of the river. And he can easily do that. And basically what he did was he found AD, and he knew because of congruent triangles that AD would be the same as AC, because these two triangles are congruent. And after that, he figured out the length of the river, and the cannons for Napoleon's army, if you've heard of Napoleon, it's like this French dude who conquered a lot of people, were able to cross the river, who were able to bombard the other side of the river and cross it, defeating the Austrians in a pretty big battle. So congruent triangles helped Napoleon win a war. So I mean, congruent triangles are pretty important. So yeah. But anyways, I thought this was kind of a funny, cool thing to talk about congruent triangles. It's very interesting. And I think that this is a cool way we can conclude today. So that story was not true, right? Oh no, the story is actually true. I'm not even kidding. Like, it actually happened. Because it's actually a common way that people do it. People find the distance to the other side of rivers. You can actually do that. But generally, people, instead of looking exactly 180 degrees, they might just look like 90 degrees. They can rotate it as however they want, but it is true. Like, you can actually do that. Though I'm pretty sure maybe it wasn't a huge war-winning thing, but it was an important battle though. I don't remember exactly where it was, but it was in somewhere in northern Italy. Yeah. So anyway, so thank you guys for attending today. It was I think this topic is pretty cool, I'm not gonna lie. So I'll put the links to the GeoGebra files in the chat. Actually, I will put it in the WeChat group and Discord server afterwards, because it's kind of a hassle to put in the chat. So yeah. So thank you guys for coming, and I'll see you guys next week, or maybe one of my friends will see you guys next week. So goodbye.